Lab 3, Black Holes and Orbits. So this lab was split into two parts. The purpose of part one was to use physics concept we've learned of curving motions, such as parallel and perpendicular components, as well as Newton's second law to create a computational model that will predict the mass of a black hole based on its gravitational force with a star of a known mass. And in part two, we use the same system using the mass of this black hole, but now there is a planet orbiting the star and a moon orbiting this planet. And in this part of the lab, we're on a spaceship, and our goal is to use a computational model to determine the initial velocity needed for the spaceship to move in an orbit around the planet and the moon without crashing into either of them. A quick review of our findings: we did find the mass to be 9.415 times 10 to the power of 33 kilograms, and the rest will be discussed later on. But first, what are some of the concepts that we needed to do this lab? So the first is Newton's second law, which we've been using in past labs. This is once again using the change of momentum with the change in time, and we've rewritten this to create the velocity formula, the velocity update formula, and the position update formula, which we use in the code later. But now we have an added component to the net force, which is its parallel and perpendicular components. So the net force is made up of the perpendicular and parallel component, which you can see the formulas down here below. And basically the parallel component is parallel to the direction of the motion, therefore it affects the magnitude or the speed of the object, while the perpendicular component is perpendicular to the parallel component, so it affects the direction, so p hat of this equation. Then we continue with Newton's third law. This is the law of reciprocity, which states that masses exert a force on each other that is equal in magnitude and opposite in direction. And this is used with the concept of gravitational force. This is M1 and M2 represent different masses, and G is a gravitational constant, which is down here. And this basically just is the gravitational force between two objects. And R is the distance between them. So how did we use these in the first part? So you can see here our initial conditions. We set G and the mass of the star is given, and the delta time is just a calculation of like all the seconds in the year. So times 60 times 60. And we start at T0. So here you can see that delta P hat is basically just we have P initial divided by the magnitude. We have all the formulas we discussed earlier are being plugged into here. So the first thing is we compute the initial momentum by the velocity, which we're given earlier, times the mass, which we're also given earlier. And from these, we keep on working through until kind of the variable that we want, because this is the mass of the black hole. So we multiply the magnitude of the force times the magnitude of the distance between the new position of the star and its origin. Divide to the power of 2, which is this basically the formula that we were using earlier, but put in this code and the while loop can be seen later. This is iterated, so we end up with our mass, which is what was given here, 9.41 to the power of 33, which we will use in part 2. But for part 1, we can see that the star follows an elliptical orbit around the black hole due to the gravitational force, and we see the changes in parallel component, changes in speed. But the closest it is to the black hole, the higher its speed or its like the magnitude. Some possible errors could be you see that the mass keeps changing when it should be the same. This might be because the G constant keeps getting changed per iteration. So we use this concept on the second part. This is where we calculate all of the different forces. So like the difference in position as well as which is used to find the force, the planet on the moon, and the ship on the moon. And this is how we find the total net force of both. Now for this, we had to find an initial velocity that worked. This is where we set the initial conditions. It was more of a trial and error. We had to try different conditions. Unfortunately, I was not able to find one, as you see the line here, that orbited around both the planet and the moon without crashing. So yes, it was difficult to find this velocity, but we did find that the spaceship has a max gravitational force from the black hole when it's closest to the black hole, and eventually the spaceship will escape the system once the speed becomes greater than the escape speed. So some possible errors, the animation made it hard to observe what's going on. and rounding in each iteration may have changed the value of the gravitational constant. So what does this mean? The first question that asked about the difference in net force and change in momentum. The answer is that they are equivalent because the net force is equal to the change of momentum over time, meaning that their components are also the same. And if we wanted to predict the motion of the entire system, we would need to include the net force of the black hole, the star, all the relation between all the respective objects, as well as the ship between we already had that one, but basically between the star and the black hole, the planet and the star, the moon and the planet, so all of that.